Protecting groups for alcohol is going to be the topic of this lesson, and specifically we're going to look at what's called a Silyl ether. And the idea is that there are certain reactions that are not compatible with having an alcohol around, and so what you're going to do is temporarily turn your alcohol into something inert, in this case a Silyl ether, and then when your reaction's done you'll convert it right back into an alcohol. So that's kind of the idea behind a protecting group. Now, this lesson's part of my organic chemistry playlist, and I'm releasing these lessons weekly throughout the 2020-21 school year. So if you want to be notified as I post a lesson, subscribe to the channel, click the bell notification. All right, so before we actually show protecting group in action, let's just show a reaction in which we actually need one first. So let's say we're going to do a Grignard reaction here, and you might recall that a Grignard reagent is both a strong nucleophile, which is usually the whole pointing at it, but it's also a strong base. And so we said last time that you can't have Grignard reagents present with alcohol as the solvent or with any alcohol around whatsoever. Well, in this case, I want my Grignard reagent to react with this lovely ketone up here. The problem is I do have an alcohol around. And so maybe what I'm wanting to have happen here in this reaction is I want my Grignard reagent to react with my ketone. So in this case as a nucleophile, and the goal then would be to form this, and then the H3O plus would eventually protonate it. Cool, and so that's kind of where, we're probably trying to go with this reaction. And so the problem is we are never going to get there because we already have an alcohol present here. And so this Grignard reagent here, once again, is not only a strong nucleophile, which is what we want it to do, but it's also a strong base. And so the truth is, it is never going to get a chance, in this case, to react as a nucleophile, because the acid-base reaction is typically faster. And so as a result, it's going to come down here and deprotonate that alcohol. So, and as a result, you're actually just going to get ketone, still going to be a ketone. You're going to form this little alkoxide. When the CH3 here bonds to another H, that becomes CH4, which in this case is methane, which is a gas. It just bubbles out of the solution. And so your Grignard's just been consumed, turning into methane, and all you've done is deprotonate your alcohol effectively, turning it into alkoxide. When you add the H3O plus, it'll just turn it right back, and you'll be back to where you started with, and you've done nothing. So in this case, we need to first protect this alcohol here in order for this reaction to work. So let's take a look at what this looks like here. All right, so the reagent we're going to use here is called trimethyl silyl chloride. There's our abbreviation, and we're going to need a base in there, and oftentimes we'll use like triethylamine or maybe pyridine, as we'll see. So, and in this case, the way this works, if we draw this out, so this trimethyl silyl ether, the silyl refers to silicon, trimethyl, that's what we got going on here, and then chloride here. And the chloride here is just a leaving group. And what we're going to have happen here is we are going to attack the silicon and have the chlorine leave. And I'm going to make this look very SN2, and you might for a second be like, Chad, you can't attack a tertiary with SN2. You can't attack a tertiary carbon with SN2. But silicon is bigger, which means these three methyl groups are going to be farther apart, and a nucleophile actually can squeeze in to attack the larger silicon. If this were a carbon, you're right, could attack it. So also, the truth is this probably actually isn't SN2. So good evidence that shows that this might actually go through what's called a pentavalent intermediate. So pentavalent means silicon would have 5 bonds for a spell. Silicon's in the third row of the periodic table, and it's allowed to go over the octet rule. And so the truth is, the oxygen probably bonds first, and then in a separate step, the chlorine will leave. So, well, before the chlorine actually leaves, we'd end up with the silicon having 5 bonds for just a minute. So, but we're not going to show that here. So we're just going to kind of show the SN2-like step, and you'll see it kind of presented both ways. And the truth is, it might even be more complicated than either of those. There might be competing mechanisms going on and things of this sort. So, but usually the mechanism is not the point of focus here. Most of you aren't even going to see a mechanism presented for this reaction. So I just wanted to make sense for you. So in this case, this will take us now to our ketone with this oxygen now bonded to silicon. Still has a hydrogen. So, and that's where our lovely base here, the triethylamine, comes into play. It's just there to deprotonate this hydrogen. So, and in this case, you might see this abbreviated. Like so, or just simply written OTMS or something like this. So same kind of thing. I just want to make sure you've seen both what it looks like in actuality as well as the abbreviations commonly used so you can relate the two. So, but this is nice. It's actually a reversible reaction. We'll find out how we can remove this when we're done, but what's nice is temporarily there's no hydrogen bonded to our oxygen. It's not an alcohol anymore. There's no acidic hydrogen down here whatsoever, and so if we had a Grignard now, it's not going to react as a base. The only option it actually has is to act as the nucleophile like we want it to. And so that's what we're going to do here. Well, I'm going to write that out just like we did here. So we'll find we've attached our new methyl group here. It's just coming in, attacking as a nucleophile like we wanted it to. So forming the alkoxide, then the H3O plus is going to protonate that. Cool, but it turns out that might not be the only thing that happens. If we make this H3O plus concentrated enough, so it turns out H3O plus is one of the couple of ways you'll learn to deprotect this. It'll actually hydrolyze this. You'd end up protonating this oxygen, putting an H back on there. So, and then you'd probably have water coming and attacking the other side and breaking the bond off, and you'd be back to having an alcohol. And so the truth is, if your H3O plus is concentrated enough, so this would already be back to an OH. So however, if it's not concentrated enough, well, now you could make it more concentrated, I guess. So, but the other thing you might do, and it's probably the more common deprotecting agents, what's called TBAF. So abbreviated TBAF, most commonly written as TBAF. You may never even see its structure formally drawn out, or at least not very often, except maybe in an explanation. So you're probably going to see that abbreviation more than anything else. So, but that TBAF is more commonly used here. And gets us back to our alcohol. Now the truth is the trimethyl silyl ether is not the only kind of silyl ether you might use as a protecting group. And the bulkier these groups get, the more you actually need TBAF. So H3O plus will work with trimethyl silyl ether. Some of the bulkier ones it won't, and you have to use TBAF. And so that's why I want to take the time to use it here. But TBAF stands for tertbutyl. Let's try that. Let's get that right. Let's draw that a little prettier. Okay, so there's tertbutylammonium, but the important part here is fluoride. Don't care about the tertbutylammonium part. This is just a way of getting fluoride ion in the solution with something big organic-y and making it soluble in a lot of organic solvents. But the fluoride is the key, and the idea is that we're eventually going to, turns out this is always going to be present with a little bit of water. So, and that water is going to protonate this oxygen here, and then fluoride's going to come in and do backside attack. So, and the idea is that fluorine forms a stronger bond to silicon than oxygen does, and so it can displace it. And so now fluorine ends up bonded to silicon, and the oxygen just ends up being bonded to a hydrogen back to an alcohol. It is now deprotected. So nifty little way to get around some things. So the idea again is that your Grignard reagent is not compatible with having an alcohol present. It would simply just protonate the Grignard, destroying it effectively. So we'll turn that alcohol temporarily into this lovely silyl ether, which is no longer protic, not going to react with a Grignard. Do your Grignard reaction, and then finally it's a reversible reaction, so you can deprotect it with TBAF or H3O+. Now, if you found this lesson helpful, would you consider giving me a like and a share? A couple of the best things you can help me do to promote the channel. If you're looking for the study guide that goes with this lesson, if you are looking for practice problems, practice final exams, anything of the sort, check out my premium course on chadsprep.com.